So what we have here is my 68,000 test rig. So there are two PCBs I've designed and had built in good old China. The bottom board, which I call the Mini 000, consists of the 68,000, or specifically the 68HC000, 1 megabyte of static RAM using the Alliance parts, I can never remember the number, 64 kilobytes of EEPROM, that is, which is the good old Atmel 28C256, a DUART, which is the XR88C681, just because I happen to have some hanging around, and a CPLD, the Max 7000 from Altera in PLCC 84. So that's the board that's underneath the top one. So that all pretty straightforward stuff, really. The topmost board is probably more interesting. The main feature, big square part in the middle, is an FPGA. It is a Altera EPF10K10, which is part of the Flex 10K series, which was a current product, probably from around 1992 to 98 or something like that. It's interesting because it's a 5 volt compatible, well they did do 3.3 volt parts as well, but there's a whole set of 5 volt compatible parts. I'm using the lowest end model, which is the EPF10K10 in PLCC 84. So this means you can stick it in a PLCC socket and use it in your 5 volt retro systems, which is pretty cool. No level shifters or anything like that needed. And the other key parts on the I/O board are the 3 lots of 32 kilobyte SRAMs and a SVGA connector and a 3-bit RGB DAC. So basically I've implemented my own VGA controller inside this EPF10K10 FPGA. It's written in VHDL. One of the interesting things about it is the console mode uses the RAM bits in the FPGA to hold the pixel data for the fonts. There's just enough. You get 3 lots of 256 bytes, which is all of the printable ASCII set, assuming you're using 8-bit wide by 8-bit tall characters. So that's pretty cool. Other parts on the I/O board are an Opal 2 or YM3812 FM synthesizer, an IDE interface, and another DUART, which is the Philips 88C. No, that's wrong. Philips 68681, which was a popular part back in the day. Philips produced a PLCC variant of Motorola's. It's famous. I think it was used in the Mac 681 DUART. That's used for the keyboard interface. So the keyboard is an AVR controller running some firmware I wrote a while back. The AVR is an 80 mega 8515, which is one of the reason you have to use that sort of part in AVR based keyboard controllers is you need lots of I/O, especially on the Amiga keyboard anyway. So pretty much every single pin of those 44 pins are used. So the other thing I've got on the table here is some breadboard, and that's used to experiment with a DAC. So I have a SPI master that's implemented inside the CPLD on the Mini ORO boards, and that's currently hooked up to an 8-bit 2-channel DAC in 4902, MCP 4902 from memory. really easy to use DAC for sound output, I've discovered. I'm sure it's used in other things, but I'm using it to generate PCM sound. I'll show you that in a minute. So that's pretty much it for the hardware. So let's quickly show you my very poor but just about usable machine code monitor. So one of the interesting features of the VGA implementation is it has hardware scrolling, so I can generate a lot of output, and instead of having to read back the contents of the screen and then write it out again offset, like you would do in, say, the Yamaha, what's the part number? I can't remember, the one that was used on the MSX. You can basically shift to the top left start address, which the display is read out of. So there we go. Dun, dun, dun. And you can see it go clunk every now and then. And so every screenful it basically has to read the bottom screen, then copy it back up to the top, and then shift the offset back to the top, and so on. But it works pretty well. Is it going to finish? I can't remember what number I put in. It's going to keep on going, isn't it? Oh well, reset. There we go. So anyway, we've got can't type today. So we can read bytes, dump out stuff as you saw, write to memory, write to ports, and we've got some simple polling without any DMA based IDE sector accesses. I haven't got a complex flash plugged in at the moment, so I can't show you that. Some routines inside the monitor for playing back VGM video game music files. Those are basically open to register dumps, and some other various things, routines for reading and writing, video memory, generating a checksum, clear screen, that sort of thing. What I've got here is this board has two serial connections back to my Linux server. And one of those is for sending over ROM images. It's basically flash, inverted commas, new monitor code, and the other one is for sending arbitrary data. Basically any binaries that I need to send from between the two machines, or for a little. So that server is running all the time on my my Linux box. And I've got a little command here called download, which can download data, give it a file path, and it will go and download it, and then you give it a memory location. But of course, we've got no dynamic memory location or anything like that, so you literally need to tell it where to stuff the bytes it gets over the serial port. This protocol is very simple. It just sends the file size, and then it sends the data. So we could dump out that data. Let's do that. Dump out the first 256 bytes of that BMP data. There you go. So there's the classic BM leading 2 bytes for the BMP. So this shows off another feature of the VGA code in the FPGA. Is code the right word? I don't know. VGA design. Zeros, yeah. So it has a very simple 1 bit per pixel graphical mode. There we go. So the only interesting thing there, of course, is that BMP files are upside down, so it needs to read the data backwards, and then it squirts it into the video memory. There you go. Shows off the hardware scrolling in video mode. Pretty straightforward. So the text mode is it's got the same feature as PC text mode in that it's 2 bytes per character. The first byte is an attribute byte. I'm trying to remember now which way around they are. And then the second byte is the actual index into the font data to show basically the ASCII value of that character square. So you've got 8 bits for the attribute, 3 bits for the foreground, 3 bits for the background, 2 bits, 1 bit for the foreground brightness and another bit for the background brightness. I think the PC has flashing mode built in, a bit like the Spectrum, but I didn't do that. So that shows the colour ability. I was quite pleased with how well that came out, considering I just picked fairly random resistor values from my DAC and just shoved them in there. So that's quite cool. I'll make use of that at some point for the command output to show, say, the dump command in different colours or something for each column. But one day. Anyway, so that's roughly speaking the text mode. There's also a register for setting the foreground and background colour. If the attribute is set to 0, which of course that's black on black, which is useless, and that can be used to invert the screen. I'm going to try and guess what that register address is. Can't be bothered to look it up in my source code, but I think it's free. I know the first nibble is free for the VJ controller. Right, that's it. So I think that should be white on black. Yeah, there we go. And you can see that the white value is not particularly great. It's not really very bright. So the resistor value is clearly not perfect, but pretty good. What else we try? I don't know. Let's go to, there we go. That's quite cool, isn't it? Bring text. No, just kidding. There we go. Oh yeah, we've also got a mode that doubles the height up as well. So all the text is, as it's basically each row is doubled. I'm trying to remember what the value for that one is now. 5, I think. I think that's bit 2. Sorry, bit 1. There we go. And doubling up the horizontal is a lot more harder, but I might do it one day. But the actual 68000 itself doesn't know that it's in doubled up mode, so the scrolling will be completely screwed. So let's switch it back. This is all just a learning exercise, by the way, in case anyone's wondering. I'm doing this for fun. Okay. The code for the VGA display is on GitHub if anyone wants to see. I'll put a link in the description. So you can download, what do we do? We download BMPs, download some PCM data now. So these raw files are basically 8-bit WAVs. They're all, at the moment, I can only play back 11 kHz WAVs. It's basically the WAV file with the leading header, which I think is 44 bytes from memory, hacked off. The location. There we go. So what's that? That's just under 32 kilobytes. 75FC. What other command to bring that back? So this command essentially loops through that memory array and writes each byte to the CPLD SPI master. Well, actually, it doesn't. It translates each byte into a word, because the SPI format is word-based, 16 bits, 4 bits of control data, and then 8, 10 or 12 bits of DAC data, whatever you want to call it, and depending on which model part you're using. So I'm using the 8-bit mode, the 8-bit version, sorry, so the low nibble isn't used. And then we have the volume. So we're going to play it at 40 rather, which is 1/4. Okay, that was Season of Oliver in Babylon 5, if anyone's remembers there. So, audio Christian. So, play it at half volume now. And if I turn my multimeter on, you'll be able to see the value at that reference, because there's 2 channels, as I think I mentioned. The channel B is used for the volume, channel A is the actual PCM data. So I'm showing on the meter channel B, voltage to ground, and on the oscilloscope is channel A. If I play it very quietly, you can see now it's at 2.5 volts roughly. Okay, now it's dropped back to 1/16 of 5 volts. Can't be bothered to get my calculator, but that should be roughly what the 0.3 volts is. So that's PCM output. Nope, I don't need to do that. So I can also play back over 2 register dumps. So I'm going to download one. I'm going to download Star Wars. I need to get this right, otherwise if I get a file not found error, I think at the moment it will just hang. It's not particularly useful. There we go. Just downloading that, which is, what's that, a little over 64 kilobytes. No, I don't want to type that. Good. Of course, this playback is interrupt based, so the computer continues to be usable. So what's happening here is every 44 kilohertz divided by 16, because I'm reducing the rate and the accuracy of the delays between each of the notes, or whatever they are, to reduce interrupt load. Doesn't really make much difference to the quality of the playback, it seems. Makes it a bit more granular. VGM is a very trivial format, just nice and easy to parse. Good old binary data, just with command bytes, so and actual registers to write to. Nice and easy. Hopefully you can hear that okay. I have got another video actually that I made a couple of months ago where I did the recording via the line in on my sound card, so it sounds a lot better. So yeah, that's my 68,000 based retro computer, whatever you want to call it. This machine is actually really just a test bed for the next machine I'm going to build, which is a single board machine with including all of these features on one board, except the Opal 2, which I'll probably pull out, and bigger FPGAs. The main reason for bigger ones is so I can attach every address bus pin and every data bus pin to the FPGA, so I can implement an MMU and a DMA controller. That's also going to be my first proper service mount board that I've designed and I will design and build. So there's going to be quite a big challenge to actually get that made. It should be pretty cool when it's done, and then I can think about system software and what I'm going to do there. Obviously I'll convert over my monitor as a starting point. After that I have no idea. I may try porting the full Linux kernel, or at least an older version of the full Linux kernel with MMU support, using my own MMU implementation if I can get that working. Otherwise, I may port my 6.9 OS, Maxio 9 OS across to the 68000. That could be pretty cool in its own right, but we'll see. It's all fun and it involves learning. Those two things are fundamental to what I'm doing here. There's no practical practical use for any of this really. It just improves my knowledge, teaches me stuff like AVRs and PCB design and VHDL and all these things that are useful, while also letting me play with some cool old technology like the 68000, which is a processor I absolutely love. Anyway, so thank you very much for watching. Cheers.